Mm. Okay, so last time we discussed the Cauchy's integral formula. So I believe so. Well, this is my opinion, but this is one. So the most important formula from the first half of this course. So it gives us well, basically it tells us well, if your function is just one time if your function is differentiable at some open neighborhood of some point, then that means you can actually have the nth derivative at the point. So therefore, well, so we were able to derive many interesting corollaries out of the Cauchy integral from that. The first one is so if f is analytic, then f prime is analytic. So therefore, infinite remain differentiable automatically. And the next corollary is well, so if your closed path integral for the closed curve is all equals to 0, then your function is analytic point. And lastly, so I guess this is the when I say undergrad student, yeah. So I remember this was very striking fact for at least for me. So every bounded entire function is automatically a constant function. So yeah. So these are some amazing corollaries of the Cauchy's integral formula. And supposedly, yeah, I am supposed to move on to next chapter on the infinite series of analytic functions. But well, it turns for me, I realized that we have like two more important corollaries of the Cauchy's integral formula, and and I really don't want to skip them. So even though our textbook says nothing about these two important corollaries, but I believe they are so important. So please allow me to spend just one more lecture on the consequences of the Cauchy's integral. Yeah. The first one is the fundamental theorem of algebra. So do you know what it is? What is the fundamental theorem of algebra? So that is suppose that you have a complex polynomial of degree n, so whose coefficient is all complex numbers. Then if you have such a polynomial, then you must be able to factor out that polynomial of degree n into n linear factors. That is the fundamental theorem of algebra. So therefore, so you don't need any more algebraic extension over the complex number. So complex number is easy. And the next important corollary is a so-called the maximum modulus principle. This is also very useful in theory and application. So yeah, I will try to keep this one by one. The first, the fundamental theorem of algebra. So it goes like this. So any polynomial of degree n. So we are assuming that n is always integer greater than 1, greater than equals to 1, has at least 1, 0 in C. Okay. Yeah. Although this statement looks a little bit different from the version that I have just introduced, but if you can find a 0 of any polynomial, then you can factor out the factor from the polynomial. So therefore, your polynomial can be factored into a b minus z0 times another degree n minus one polynomial, and so. And if you continue this procedure on and on, then you can actually factor out this entire polynomial into linear factor. All right. So in order to prove this, I need a little piece of lemma. So And lemma goes like this. I have a polynomial that looks like this. A0 plus A1Z plus A2Z2, all the way up to AN, ZN. So this is a degree n polynomial. And well, we are assuming that AN is a non-zero number, which is very obvious. So be a degree n polynomial. Then is a, as then I must be able to find a positive real number such that if the modulus of the complex number is greater than that number R, then the modulus of the reciprocal of this polynomial is bounded by this number. Okay, so before I try to prove this, so let me try to give you some explanation of this. Once you have the polynomial, then you can expect some zeros of the polynomial, right? And if your z is getting really close to zero, when your z is getting really close to zero of this polynomial, then the modulus of this reciprocal will be approaching to infinity, right? So therefore, so because of the reason, my positive real number R must be large enough so that inside of the disk with center 0 and radius R, this disk must contain all the zeros of this polynomial, right? And eventually then, so therefore, when the outside of this disk of radius R, then there should be no zeros. Then therefore, the magnitude of the reciprocal of this polynomial will eventually die out to zero, right? So this is the idea. So for me, so this is very obvious statement for me, right? So if you can choose such a large enough, so if you can choose a large enough positive real number R, then this should be true. But yeah. This is just my intuition, and let me try to give you the rigorous proof of this guy. I have a this is my polynomial. Then this leading term, a n z n. So I'm going to move this guy to this side of this equation, so that I have a n minus 1 times z n minus 1. Okay, so now I'm going to play a little algebraic trick on the right-hand side of this equation. So I multiply everything by z to the nth power, and a0 over zn plus a1 over z n minus 1 a n minus 1 over z. Right. And for our future purpose, yeah, I'm going to give the name of this vector. So I'm going to say this guy is W. So W times okay, so this side is this, and this is Z times W. So, okay, sorry. I got confused. So this is just simply z to the n times w. All right. Now I want to consider the moduli of these two sides of equation. Taking the modulus of this side, sorry. So the modulus of the w times z to the n is by triangle inequality. So a0 plus a1 and z a n minus 1 times z to the n minus 1. All right. Now what? Dividing the both sides of this inequality by z to the nth power, then a0 over zn and a1 over z n minus 1 a n minus 1 over z, yeah, I guess. Now what? Now I will need to choose the upper bound of this entire, well, I will need to choose the upper bound of this number w, the modulus of w. So like this. I am letting that r to a, so I will define a number. So ak over z to the n minus k. So times 2 times n. N is the degree of this polynomial, and everything taken by n minus k square root. So this is just regular square root. So that we did in the real analysis. And clearly this is a positive number. Okay. And also I have such, so I have just n such numbers. This index n varies from 0 to n minus 1. Yeah. So if k equals to 0, then this is the first term. And if k equals to n minus 1, then it's going to be the last term. Now, I will define a number. This is going to be the maximum of all such numbers. R0, R1, R n minus 1. Yeah, there must be such a number. All right. So this is the R that we are looking for in this statement. So if the ZE lies in the outside of the disk of the radius R, then each of these guys, AK over Z to the n minus K, is right? Yeah, sorry. Well, so R to the n minus K, because this guy is greater than this, so therefore this one is bounded by this. And well, then also since my R was chosen from the maximum of these numbers, so since R is greater than RK, so I have this inequality over here, but RK was defined to be this. So if I just raise n minus k's power of this number, then this is going to be AK over, what is this? Yeah, I have to be careful, extra careful. So AK times 2n, everything by Sorry. Yeah, I messed up. My bad. This one is supposed to be an, the leading coefficient of this polynomial, n minus k. Yeah, sorry. Yeah, I made a mistake. So ak times 2n by a n, and I don't need this. Yeah, sorry. Oh, sorry. Somehow, yeah, I am making lots of mistakes. Sorry about this. Okay, good. Then this is an over 2n. All right. Yeah, sorry. Yeah, so this one is the right expression. Okay. Yeah, this was kind of technical lemma. Okay. So what now? So if z is greater than, the modulus of z is greater than r, then each of these terms on the right hand side of this inequality is guaranteed to be less than equals to 2 an over 2n. So this implies, and we have n such terms on the right hand side of this. So this is n times an over 2n. So eventually just an over 2. Okay. All right. Okay, so finally we have the upper bound of this number, mysterious number w, and okay, all right. So now let me go back to this expression. This guy equals to z at z to the n times w. So since pz minus the leading term was w times z to the n, so pz is an plus w times z to the n. Now what? So I am supposed to find some bound of this number, because yeah, if I can find the bound of this number, then that bound of the modulus of this number, then that means I can find the bound of the reciprocal of this polynomial. So an is an plus w minus w, right? And by triangle inequality, an plus w plus w, right? So an plus w is bounded below by an minus the modulus of w. But if z is greater than, the modulus of z is greater than r, then we have this inequality. So that means this guy is just an minus an over 2. So which is just simply an over 2. Okay. Yeah, so this is good. Okay, this is good. This is right. So now I have found the lower bound of this guy. So the modulus of this polynomial is it's modulus of an plus w times z to the n, but this is an over 2 times z to the n. But since we are constantly assuming that the modulus of z is greater than r, so this guy is also bounded by this one times r to the n, right? And I guess we are done. So, and taking reciprocal of everything, then just 1 over PZ is bounded above by so 2 times AN times RN. Okay, great. Okay, so now we have the lemma, and finally we are ready to prove the fundamental theorem of algebra. Okay, so what is the best way to prove this? What is the best way to prove the fundamental theorem? So since we are assuming, so since the statement says that we can find at least 1 zero of the given polynomial, so I'm going to prove by contradiction. So suppose that there is no such a zero for the degree n polynomial. So suppose not, then PZ has no zero. Then, okay, then, well, clearly this is a polynomial, so therefore, obviously this guy must be analytic function. So, and once analytic function doesn't attain zero, then 1 over that analytic function also must be analytic, right? So 1 over P of Z also must be analytic. And how can I derive a contradiction from this? Oh, okay, good. Yeah, now I remember. Then this function is analytic, and if analytic function, then clearly the function must be continuous. So this guy is also continuous. Okay, so this positive number R is the R from this previous lemma over here. So this guy is continuous on this one. So here, over here. So that means, so if any continuous function, so this is a continuous function on some closed and bounded set. So therefore, you must be able to find the maximum value of the modulus of this. So this guy is bounded. And also, this reciprocal is also bounded on the outside of the disk of radius r. Why? Because, well, since we are enjoying this inequality, so this implies that this 1 over this polynomial is bounded by this number, right? This is just some definite positive number. So that means this is also bounded. So so inside or outside, this function is also bounded. So therefore, this guy must be constant. Then now I know this is a contradiction, right? Because we are assuming that this polynomial was a polynomial of degree greater than equals to 1. So it cannot be a constant. But clearly says this one has supposed to be constant because the Liouville theorem. And if 1 over z is constant, then that means that z is also constant. Okay. So great. So this is about this. This was the fundamental theorem of algebra. This is also amazing that fundamental theorem of algebra. So there are actually many different ways to prove the fundamental theorem of algebra. But I really like this theorem. I really appreciate the argument of this theorem because it really made use of the unique property of the analytic function in the complex term. And the next thing is so-called the maximum modulus principle. So what is the maximum modulus principle? So if you have an analytic function, well, the modulus of your analytic function may be different. So unless your analytic function is constant, and the maximum modulus principle tells us the maximum modulus of your analytic function cannot attain the interior of your domain. So that means if the maximum modulus of your analytic function is somewhere attained in somewhere, and that point must be always on the boundary of your domain, not inside, not the interior, but only on the boundary. So that is the idea of the maximum modulus principle. So in order to prove this, again, I need a little piece of lemma. We consider a small disk of radius epsilon. So I say d epsilon of z0. So what is this? This is a subset of complex numbers such that this is nothing but a disk of radius, open disk of radius epsilon centered at the point z0. Okay. Now, suppose that I have an analytic function on this disk of radius epsilon, and this is a very crucial assumption. Suppose that the maximum modulus of this function is attained at the very center of this disk of the radius epsilon. Then for all z in the disk, then the conclusion is then f must be constant. So basically, if the maximum modulus is attained at the center of this disk, then your function must be constant. There's no other way. So this is the only possible option. Okay. All right. So I want to draw a picture. This is the disk of radius epsilon. So d epsilon with center 0. And so at the very center of this, I have a point of z0. And the radius of this guy is epsilon. And here, what I want to do is this. I want to choose any number. So I'm going to say it low between 0 and epsilon. And now I want to define a CP, which is a curve. I should better say this is a circle with radius rho. Center is the point, the center of the disk, z0. So, so it must be like something like this. So yeah. So this is my new center. This is my. So this blue one is C of rho. So we are talking about, so we'll be working on this circle. So obviously, so we are assuming that this circle is positively oriented. And I'm going to use the Cauchy's integral formula. Integral formula. I want to evaluate the function value at the very center of this circle, which is just 1 over 2 pi times I, and with C low goes here, and f of z by z minus z0 dz. So this is the Cauchy's integral formula. All right, good. So now I will try to compute this integral in explicit manner just by introducing the parametrization of the circle C low. So what parametrization do I use? Here we are using this parametrization. Z is z0 plus rho times e to the I theta. Where clearly the theta must be a number between 0 to 2 pi. Then yes, 2 pi I just carries over. And from 0 to 2 pi, f of z0 plus rho times e to the I theta. And for the denominator, this is my z. If I am plugging in this guy to the bottom of this fraction, then this z0, they just cancel each other. So I will have just rho times e to the I theta and times the z dot, which is nothing but the derivative of this parameterization with respect to the theta. So which is I times rho times e to the I theta, and everything by d theta. Okay. All right. So I have two rows on the bottom and the top here, and I have one I over here, over there. So they just cancel. So this is going to be just 2 pi times integral from 0 to 2 pi and f of z0 plus rho times e to the I theta, everything times d theta. Okay. Okay. Yeah, I had just ended up with very interesting conclusion. Yeah, my proof is far from done yet, but I want to emphasize this. What is this? So let me just focus on this side of the equation. What I'm doing, what I'm attempting on the right-hand side of this equation is nothing but the line integral of my function f along with the circle C of rho. So 2 pi times f z0 plus rho times e I theta and d theta. So what does it mean? So I have a circle. This is my center of circle, z0. And this is the circle, which is enclosing the center of this circle, z0. And this theorem actually tells us the function value at this point, the center of this circle, is completely determined by the integral over the circle of any radius, right? So, well, maybe I should better say something like this. The function value at the center of this circle can be written as the average of the function value around the circle, C of that, right? Yeah, I am taking integration, and this is the right. This is the interval integration, and I am dividing everything by the length of this interval. So this is precisely we are just talking about the average function value along this line. So this is what we say the Gauss's mean value theorem. Just one more thing. So this is f of 0. Then, in other words, 2 pi times here. This is the right side. Sorry about this. Yeah, I can also paraphrase this integral like this. Like this. Sorry. Yeah. So what is this? What does it mean? So if your function is analytic, then very strange thing happens. So, well, okay, let me just focus on this integral. I am taking the difference between the function value at this point and the function value at this point, the point of the circle. And if you just integrate this difference of these function values along with the circle C of rho, then the average value of this difference of these two function value equals to 0. This is exactly the idea of the harmonic function. Do you remember this? The idea of the harmonic function actually can be very well described in this Gauss's mean value. Okay, all right. Yeah, I was so excited. So yeah, I really want you to emphasize this Gauss's mean value. All right. So anyway, that's that. So, okay, all right. So now we have the Gauss's mean value theorem, and what I want to do is I want to take the modulus of the moduli of two sides of this equation. Taking the moduli, then the modulus of this f of z0 is modulus of this guy, but this is clearly greater than, this is clearly less than everything by the theta. Okay. This is easy. Okay, now what? Yeah, oh, right. Now this is time to take advantage of this hypothesis. Since the maximum modulus is attained at the very center of this circle, the very center of this disk, so this integrand over here must be bounded above by the f of z0, right? Okay, great. So this is 1 over 2 pi, and I should better put the modulus over here. So f of z0 and d theta. Now this integrand is just constant. So what I need to do is just multiply this number by 2 pi, but dividing by 2 pi means this is just modulus of f of z0, right? Right. So this number, this guy is bounded. This number is bounded below by this and bounded above by this. So therefore, this number must be precisely this. Okay. So f of z0 is just this guy. Now moving everything to the other side, 2 pi. So maybe f of z0 minus f of z and everything, the big parenthesis and d theta. And everything must be z. Right? No, this is okay. All right, great. This is constant, and for this guy, my functions, we are assuming the function is analytic. Therefore, this function must be constant on this circle. Therefore, this integrand must be a continuous function, right? This integrand is continuous function. And well, at the same time, since this function value, this modulus is supposed to be, because of our hypothesis, this guy is the maximum modulus inside of this. Therefore, this integrand must be always non-negative. So this integrand is continuous and non-negative guy, and integrated over this interval and equals to 0. So therefore, the only possible explanation is this integrand must be identical. So this is continuous and non-negative. So f of z0 is in other words, the f of z0 is the same as f of z. Sorry, the modulus of f of z0 is the same as the modulus of the f of z, where z is any point on C of rho. Okay, so what is my conclusion then? So the modulus of this point is the same as modulus of any point on this circle, right? But however, so you have to remember that this choice of rho was completely arbitrary between 0 to epsilon. So therefore, that means, well, under this hypothesis, my function value of the modulus of any function value in this must be the same as the modulus of the center of this. So f of z0 is just f of z for all z inside of this disk of z0. Okay, so am I done? No. What I have proved was, so this function value, so we proved the moduli of all these points, all the moduli of all the function values inside of this, they're the same. But that does not guarantee my function is constant. Well, in complex numbers, there are many different complex numbers that share the same moduli, right? So So in order to prove that f is constant on the disk, then yeah, I'm gonna need proof just a little bit more assertion. If f, I have function f, and the f bar, so which is the complex conjugate, so u xy minus I v xy, if they are both analytic, on some domain D, then f must be constant. All right. So how do I prove this? Well, maybe I can use the Cauchy-Riemann conditions. By Cauchy-Riemann conditions on the analyticity of the function f, ux is vy, and uy is minus vx. Well, then, well, yeah. To avoid confusion, so f bar is just, I would just say f bar is large U plus I times large V. Yeah, obviously, large U is the same as small u, and large V is just simply minus of small v. Then, well, since we are assuming that f bar is also analytic, so this large U and large V, they must satisfy the Cauchy and Riemann conditions. So again, by Cauchy and Riemann conditions, ux is large vy, and large uy is minus large vx. But you know, this is the same as small ux is minus vy, and small uy is plus vx. Okay. Okay, what now? Okay, ux is vy, but at the same time, ux is minus vy. So therefore, ux must be identically 0. So ux identically 0. And what about uy? So uy is minus vx, but ui is at the same time vx. So, sorry. uy is also identically 0. And what do we know from here? And the f derivative is, well, ux plus I times uy, sorry, vx, but ux equals to 0 and ui 0, that means also vx equals to 0. So this is just identically 0, right? Well, and also, well, long time ago, you should be able to remember that if derivative of any complex function equals to 0, then that function must be constant. So. Okay. Okay, now we are ready to prove the lemma. So now we know that the f prime, so modulus of fc is constant for all z in this disk. But this condition is the same as the modulus squared equals to c squared. And this is fz times the complex conjugate of fz is c squared, then f the complex conjugate of fz is the c squared over fz. Okay. All right. Oh, by the way, I need to assume that without loss of generality, I assume that c is a non-zero number. Why? Because if c equals to 0, then that means but if c equals to 0, that there is only one such complex number whose modulus equals to 0. So this automatically guarantees that fz is constantly 0 function. So there's nothing to prove. So we should say that c is a some non-zero number. So if c is a non-zero number, then fc, the modulus, then that means this number, this complex number f of z can never be 0, right? So that means since if this guy never attains 0 on this disk, so that means this function is also analytic. Because why? Because we are assuming that this guy is analytic, and so this is analytic. So therefore, the complex conjugate of f of z is also analytic. Right? So f is analytic, and f bar is also analytic. That means f is constant. So f is constant on the disk. Okay. Okay, so this lemma is done. Now I am finally ready to prove the maximum modulus principle. This is so-called, this is the maximum modulus principle. So it goes like this. I have a function which is analytic. And suppose that this is non-constant. On a open connected set D, then fv has the modulus of f of z, no maximum value in D. You should remember that domain means open and connected. So that means so therefore D being a domain implies that D doesn't contain its boundary point. Therefore, so the maximum modulus can never attain the interior of the domain. Okay. All right. A little piece of trick is required to prove this. Well, suppose not. As always. So suppose that there is a point z0 in D, such that the modulus of the function value at z0 is greater than equals to the modulus of the function values of all other points. Okay, all right. So since I tried to prove by contradiction, somehow I will need to derive a contradiction. So yeah, okay, all right. So I will try to prove that under this hypothesis, I will prove the function is a constant. Okay. Well, let me say this is ugly domain. Is this ugly slime is my domain D, and this is my point z0, and I just choose a random point, which I will call P. choose any point P in D. And being domain means that this open set is also connected. So therefore, I must be able to find a piecewise smooth curve from Z0 to P, like this. And what? All right. So there is a curve, I would say L, from Z0 to P. And I want to define a number, this guy to be the infimum of the module Z minus W, which is Z is a point in D, and W is on the boundary of D. Well, in the case when this D is the entire complex plane, then D just can be just any other number. But for most cases, my domain D may have a boundary of itself. So what is this number? So we are just taking, Z is any number. Oh, sorry, I messed up. Yeah, this one's supposed to be L. Yeah. So we are just measuring the distance between a point on the curve and the point on the boundary. And the shortest such pair of points can actually make this distance D. Okay. So so therefore, just take a union of all the disk of radius D with centered at any point on this curve. So, and this choice of D guarantees that, union of all such open subsets will be contained completely inside of this domain D. Now we choose a sequence of point Z0, Z1, all the way up to Zn, and this Zn is the same as the final point of the curve P, such that every point must be a point on the curve. And condition number 2 is the distance between two adjacent points must be less than D. So, so what are these? So what is the point of just such a sequence of points? So this is something like this. So, this is Z0, and this final point is Zn, and Z1 and Z2, Zn minus 1. So, sorry. My circle needs to be slightly more bigger than this. And let me say, the radius of this disk is D. So this is the radius of this disk. And because of the condition number 2, so inside of this disk, centered at Z0 with radius D, the next point is also included in this disk, right? And the same thing is true for the next one. So now this is another disk which is centered at the second point, and the next point is also included in this the second disk, right? So it goes on like this. So, and finally, no. Mm. Yeah. Okay. So you can consider this well, n many disks, and each of these disks will contain at least 2 points, two consecutive points. Well, I'm gonna call each of these disks n0 and n1, and n of n minus. So also n of k is a disk that I have just defined, and z minus zk is less than d. K is from 0 to n minus. All right, yeah. Okay, so let me begin from the first open disk, n0. This is open disk, and since we are assuming that the modulus of the function value at z0 is the greatest, therefore on this open disk, by the previous lemma, so the function my function on this disk must constant, right? So that means the function value at this point must be the same as the function value at this point. By the lemma, since fz0 is greater than or the point is greater than or fz for n0, so f is constant on n0. So that means fz0 and fz1 must share the same value, right? So this guy and this guy must have the same function value. And yeah, I can apply the same trick on the second open disk n1. On the second disk, well, since this guy was the function value, the modulus at this point, which is assumed to be which is the same as the function value at this point, and the modulus of this point was assumed to be greatest. Therefore, the modulus of this point function value right here also must be greatest, right? So therefore, since the modulus at this point, that this center is the greatest, therefore, the function f must be constant all over the second circle n1. And we can proceed like this. So eventually, it turns out I am safe to say that the function value at this point is the same as the function value at this point. So f z0 is f of p, f of zn, which is f of p. Okay, so this implies that my function must be constant. Just contradiction. So, well, this is this is the maximum modulus principle. But my favorite version of the maximum modulus principle is like, suppose that you have a closed and bounded set of the complex plane, and if your function defined over there is analytic, the maximum modulus always attained on the boundary of that closed and bounded. Why? Because, well, since your function is analytic, so therefore, the function must be continuous, and continuous function on some closed and bounded set must attain the maximum value at some certain point. Therefore, if there is a maximum value, then the maximum value must be attained on the boundary. So suppose, okay, so yeah, maybe I'm good to skip that. Yeah, so this is just tiny little exercise about the maximum modulus principle. This is I, and this is 2. Okay, yeah. I have a very silly looking right triangle over here. One vertex on the origin, and the other vertex at 2, and the last vertex is on the I. And I want to find the maximum modulus of this guy. Where can I find the maximum modulus of this one? Can you figure this out? Well, this is the modulus of my function. And for me, this one looks like the distance between a point on this right triangle R and the point right over here, the point -1. So so if I can find the maximum distance on this triangle from this point, then that is going to be the point where I can attain the maximum modulus of this analytic function. And as you can clearly see from this guy, the maximum modulus is attained exactly at this point. Okay, yeah. So as we expected, the maximum value is attained right over there. What about the minimum modulus? Minimum modulus is also attained at this point, right? Yeah. So maximum modulus is at z is 2. Okay, so well, this is the end of the maximum modulus principle. But well, I will need to say a little bit more on the harmonic function, the maximum modulus principle of the harmonic function. So why? Okay, why do I even care about the harmonic function? So, well, if you have studied some differential equation course, then you can easily convince yourself that this is the this is a heat equation. This is the heat equation. And suppose your system is at the thermal equilibrium. So thermal equilibrium, that means that the temperature doesn't change anymore. And at each point of the system, the temperature doesn't change anymore. That means this cycle is 0, right? So when your system is at the thermal equilibrium, then that means your function is the harmonic function. The solution function is the harmonic function. And so a study of the harmonic function is especially very useful. So when you're studying the differential equations, and the maximum modulus principle can also be expected for the harmonic function. Okay, I'll try to explain one by one. Well, suppose I have a function, so which is 2 variable functions is harmonic. And well, for simplicity, let us assume that this is simply connected. And in this condition, under this assumption, then every such a harmonic function can be considered as a real part of some another analytic function. This is, why is that? Because so U is harmonic. Well, yeah, sorry, yeah, sorry, yeah. Let me change my mind. I will say this H. Since H is harmonic, so HXX plus HYY equals to 0. Then now we assume that now we consider a function which is defined to be HX minus I times HY. And I say this guy is satisfying the Cauchy-Riemann condition. Why? Satisfies because this guy taken derivative with respect to x is, this is my imaginary part taken derivative with respect to y, and also the real part with respect to y is the minus the imaginary part of x. Okay, yeah. So every harmonic function. So if I define a function something like this, then f is analytic function on the domain, and so f is analytic. Therefore, so therefore every every path integral on the closed curve must be 0 in this domain. Therefore, this f must have the antiderivative, right? So f has an antiderivative f. So let me say if f is u plus iv, then f prime is ux plus I times v x, but this is ux minus I times uy because of Cauchy-Riemann equation. But this is hx minus I times hy, because this guy must be the same as small f, and this is our definition of small f. So that means hx is ux and hy is uy, right? Comparing these two guys and these two guys. So what do we know? So h must be uxy. Okay. So therefore, every harmonic function is a real part of this guy, right? Because this turns out to be precisely h. Okay. Now what? And if you have the analytic function, if f analytic, then the exponential of f is also analytic. Therefore, the maximum modulus principle also can be applied to this function. But what is the modulus of this guy? The modulus of this guy is, sorry, I should better say large f. But e, which is just e to the large u, which is e to the h. Okay. So maximum modulus, according to maximum modulus principle, the maximum value of this guy is only attained on the boundary of this region, right? And once the maximum value of this guy is attained on the boundary of this region, therefore the maximum value of h is attained at the boundary level. All right. All right, so this is it. And see you next time. And 추석 잘 보내세요.